Number 6 in 2019 here, this was the question. It says functions f, g, and h are twice differentiable functions. We also know the values of g and h at 2. So they both have the point 2, comma 4 on the graph. And this is the line that's tangent. So you have to understand what they're giving you there. So this is our tangent line. If we plugged 2 in, we would get 4, so there's nothing tricky there. But this is the line that's tangent to both the graph of g and the graph of h. So what this is telling us is this is our slope right here, right? So if this is the slope of the tangent line and it's at the point 2, then we would know that the derivative or the slope at 2 is equal to 2/3. And that is all you would have to write. There's nothing to really justify there. You just have to be able to pull it from the question. So part A is just 1 point. We're going to move on now here to part B. Let A be this function, so we're going to be using this. Write an expression for the derivative at x, and then we're going to find what it is at 2. So we just want to go ahead and I would use the product rule, and I'd put my product right there because we have a constant times x cubed is one chunk, and then h of x is your other chunk. So if we want the derivative, we're using our product rule. I'm going to leave the 3x cubed alone first, and then times the derivative of this would be h prime of x plus, and then I'm going to leave the h of x alone, and whether you do that in the front or you wait and do it in the back, it's up to you. But I'm leaving h of x alone, and then the derivative of 3x cubed is going to give us 9x squared. So that's an expression for the derivative. And then what we need is we need what it is at 2. So I'm going to plug 2's in wherever I see an x. So this would be 3 times 2 cubed times h prime of 2, which we'll find that. Then plus 9 times 2 squared times h of 2. Okay, and we already know h prime of 2 is 2/3. So we have 8 times 3 is 24 times 2/3 plus 9 times 4 is 36. And then h of 2 we know is 4. And you can circle this answer. You could even leave it messier than that with what we have before there. If we clean this up, we would get 160. So if you did that, that's what you would end up with there. And your points there, a form of the product rule. So showing that you know the product rule gets you a point, and then another point is for the derivative of a at x, so coming up with this exact equation here. It seems like those 2 points kind of go hand in hand. And then the third point is this value of 160, or what we have circled here. Okay, part C is kind of flipping our L'Hopital's rule and how we usually solve these, and it's making it so we really have to understand what's going on here. So you just want to start doing something. You know, for L'Hopital's rule that it's either going to be like a 0 over 0 or a plus or minus infinity over a plus or minus infinity. And we're trying to find the limit as x goes to 2 of h of x. And h of x is this here. So I'm going to put that into its spot. So we've got x squared minus 4 over 1 minus f of x cubed. So if I plug 2 in doing my direct substitution, I would get 0 on the top. So I want this to be 0 on the bottom so that I can apply L'Hopital's, because it says it can be evaluated using L'Hopital's. So in order for this to be a L'Hopital's problem, we know that we would have to have 1 minus that f of x cubed would have to equal 0 in order to get us that 0 over 0 that's needed for L'Hopital's. And then if we solve this, I would add the f of x cubed over, so then I would get 1 equals f of x cubed. And then if we take the cubed root of both sides, we'd still have 1 equals our f of x. And what's one of the questions, and I should put 2 in here instead of x really, because I'm doing my substitution of my x is 2, so I should replace these with 2's. Here we go. So what I end up with is that f of 2 equals 1. And that's one of the things I wanted. Use this limit to find f of 2. So I've got my f of 2. So even if I can't get the other part, I've got part of my answer here. But then the other thing that we can do is actually try to maybe apply L'Hopital's. And we're going to see what happens because I feel like, you know, sometimes we try to think through it a lot and we can't get there because we're not seeing everything. If you start writing some things down, sometimes that helps. So we're going to go ahead and apply our L'Hopital's and see what we get here. So if we apply L'Hopital's, let's see, we got our 0. I got to think about what's going to happen here. I'm going to start a different color. So we got our 0 over 0, so then L'Hopital's, therefore, there we go. So the derivative of the numerator is going to give me 2x, and the derivative of the denominator, the 1 goes away. This, we pull the 3 down, we have negative 3 times f of x squared, and then you have to take the derivative of the inside, so times f prime of x, and this is where hopefully we'll be able to find what f prime of 2 is. Okay, and what I'm thinking here is I'm trying to figure out, okay, what does this limit equal? We're talking about the limit of h of x, and we know that h of 2 should give me 4. So because this is twice differentiable, that limit should go to 4. There shouldn't be like a weird break in the graph where the left and right hand limits are doing different things. We shouldn't have any of those type of issues. So we want this to equal 4. And if we plug in 2 for my x's, in the numerator, I'm going to have 4. In the denominator, I'm going to have negative 3 times f of 2 squared. And f of 2 is 1, so 1 squared would just be 1. And then times f prime at 2. And this should equal, I'm going to say 4 over 1, and then I can cross multiply. You could just have it equal 4 and multiply this piece over, however you want to think about it. But really, when I see this proportion, if the numerators are matching up, these denominators have to match up. That's another easy way to look at it. So we get negative 3 times f prime of 2 equals 1. So f prime of 2 would equal negative 1/3. And I would say that would be a question that most people probably wouldn't get the second part to. Maybe the first part. The first part's kind of tricky because you haven't seen it presented like that before. Okay, now this one, looking at the key, I'm just going to drag it. Okay, here's the key for part C. So there's 4 possible points. So it says if you realize that the limit was going to equal 4, that was a point. So I did that. Well, I suppose I didn't even do that up here. Well, yeah, I did. Really, I said the limit's going to equal 4. I just did it after that first step. So I would get this point right here. F of 2 is equal to 1. That's another point. Obviously, the f prime of 2 equals negative 1/3. That's another point. And then doing L'Hopital's rule correctly, where you get 2x in the numerator and you apply that chain rule and everything. So you do the derivative of the numerator and the derivative of the denominator. That's going to give you your last point there. This question kind of surprises me because I have never seen this on the AP test before. The concept itself is not really crazily difficult, but actually they used the squeeze theorem, it's called, and I used to teach it all the time, and then it never showed up on the AP test, so I took it out of the curriculum. I think I mention it now, so you probably have heard of the squeeze theorem. It's something I used in college quite a bit, so I like to mention it. But if you didn't say it by name, I think you'd probably be okay here. So with this one, it says it is known that our g of x is below our h of x or equal to it from 1 to 3. So if we just think visually here, from 1 to 3, We've got our h of x maybe is up here, and our g of x is maybe down here. Now we know at 2, they're equal to each other. So at 2 here, they're going to be equal. So maybe g is like this, and then goes up, and then comes back down, something like that. We also know that these two functions are differentiable. So they're also going to be continuous. It's not like there's a break in those graphs. It says let k be a function that's between those. So it's squeezed between those. That's the squeeze theorem for 1 to 3. Is k continuous at 2? So it's saying, does it have to be continuous here? And the answer is going to be yes, because if these ones don't break and that one's in between it, it's also going to have to stick to that same value. So let's look at the answer and how they wrote it out. Just because we have not worked on the writing of this. So because G and H are differentiable, they're continuous, so we said that. So the limit of our G of X is going to be 4, and the limit of our H of X is also going to be 4 at that spot. And then because this one's in between those values, because of the part that they tell us right here, it follows from the squeeze theorem that the limit of K of X also has to equal 4. So they're all going to equal 4 at 2, thus K is continuous at 2. I would kind of wing that one. I wouldn't like spend a bunch of time memorizing it or have like the squeeze theorem written off to the side because you have so many other notes to deal with, and I have not seen that before in my, dozen years of teaching. But the concept itself, you might be able to pull off that point. Realize it's only 1 point too, and that's 1 point out of 12 years. It's not like it's a crazy hard question, but it wouldn't be something I would focus too much